So we're going to begin by looking at the idea of a metric, or also known as a distance function. Distance function. And so we'll just look at an example which should all be familiar with. If we take, for example, the 2D plane, and we have a point x with coordinates x1, x2, and we have another point y with coordinates y1, y2, then we can calculate the distance between these as a function. Let's call it d. So I'm just using d of xy to denote the distance function between the point x and the point y, and this is equal to the root of x1 minus y1 squared plus x2 minus y2 squared. And so let's just analyze what's exactly happening here. We're taking a point in the plane and another point in the plane, and we're outputting a real number. So let's just write that down. So the d is a map from r squared cross r squared into r. See, this is a value in the plane. This is a value in the plane. And so what happens if we want to generalize the idea of distance to just any set, just any, I mean, you can obviously see how this would work for a three-dimensional space or n-dimensional space, but what if we just want to take an arbitrary set and define some notion of a distance on it? Well, we can begin by just, replacing the set where we're taking the values from. So we'll start by defining an arbitrary metric d from some set x, two values in a set in some set x, and giving us a real number which will be the distance between them. So, but this isn't enough, right? We need more restrictions on this, because there's properties, there's aspects of this idea, this distance idea, which we want to preserve. Like, for example, it wouldn't make any sense that a distance was ever negative. If you travel from point to point and you realize that you traveled a negative distance, you'd probably be a little bit confused. So let's just write down some of the conditions we want to impose on our general definition of a metric. So let's call this number 1. We want that the distance between 2 points is 0. So there's no distance between 2 points if and only if they are the same point. And let's just draw this on our concrete example, which we were using up there, the 2D plane. If we have a point x which is the same point as y, then obviously these have no difference between no distance between them. And if there are 2 points that have no distance between them, then they must be the same point. Otherwise, there would, if they weren't the same point, then there would obviously be some distance between them. So this is a property of the Euclidean metric on the plane that we want to preserve when we define our abstraction for a metric on any set. So let's do another one. The second axiom or condition we want to impose on our metric is this is called symmetry. Is that the distance from x to y is equal to the distance from y to x, and this is definitely a property we want to have when we're talking about a distance function, right? If we travel in one direction from say say this is a point z. If we travel in this direction, then we want that to be the same distance as if we travel in the other direction. So this is what this property of symmetry defines for us. So the last one, this is called the triangle inequality, and probably everyone's seen this at some point, is that if you have, say, the distance between a point x and z, this is always less than the distance. So we're traveling from x to z, say. To think about it that way, if we travel from x to z, then this is always a shorter distance than if we had traveled from x to any other intermediary point y, and then gone from y to z. And it's called the triangle inequality because you can see this makes a triangle if we say this is x, and we're traveling to z, and take any other point, doesn't matter where it is, say here, y, then this distance is less than the total sum of this and this distance. And we'll prove this formally in the next video when I do some examples, but for now, this is called the triangle inequality, also known as subadditivity. So you may be thinking, well, earlier I said that, well, non-negativity, that the distances between 2 points was never zero, was something we wanted to put in a property we wanted for a general metric, and I haven't actually done that here, but the combination of these three things actually implies this, so I'll prove this down here. So this comes from taking, if we take the triangle inequality and just let x equal z, and I'll do some diagrams. So if we just let x equal z, so this is the distance between x and x is less than or equal to the distance between x and y plus the distance between y and x. So what does this actually mean visually in our example with the plane? So if we have our plane, then what it's saying is if this is x and this is y, then the distance between x and x, just traveling from x to x, obviously being 0, is less than the distance of traveling to any other intermediary point and then back again. This is these two things. So what we have here is that, I mean, obviously this thing is equal to 0, and these things are equal, both of these, because of this this second law here, the symmetry. And so what do we have ultimately here? We have that this two of these, so 2 times the distance between x and y is greater than this, but this is equal to 0, so this is greater than or equal to 0, and let's just get rid of this factor of 2 here, and we have that the distance between any two arbitrary points, x and y, in a general metric is necessarily non-negative. And in the next video we'll do some examples of different kinds of metrics.